Hello friends, in this short video, we will be discussing about Hall effect. This is different from previous topics that we were discussing on semiconductors through our video series. Here we will see what happens when a magnetic field is also applied along with electric field. In order to understand what Hall effect is, let us consider a semiconductor wafer as shown in the figure. It is being connected to an electric field V of x. A battery is being connected V of x, so that there is an electric field in the x direction Ex, and due to this there will be movement of carriers. Let's consider the electron carrier alone. So that since the electric field is in x direction as shown in the figure, the electrons are moving in the opposite direction. Now, suppose that we keep this setup in a magnetic field such that there is an effect of magnetic field BEZ perpendicular to that of the direction of electric field. Because of that, the electrons moving in the wafer will experience a deflection. If this deflection is to be curtailed and this electrons has to move as earlier, there should be an electric field which opposes the magnetic field effect. Generation of such an electric field is known as the Hall effect. We will see more detail of this in this discussion. As I had mentioned, if a magnetic field is applied perpendicular to the direction, here they have taken, or here we are going to take that of holes rather than electrons. Any one carrier can be considered. So we are considering holes. In the p-type bar, we are taking a p-type bar so that the majority carriers are holes. The path of the hole tends to deflect. And this force can be mathematically represented as F. The force is equal to Q into electric field plus drift velocity into magnetic field. So specifically, if you are taking in y direction, we will have a force Fy, which is Q into Ey plus Vx into Bz. And unless there is an electric field is established along the width of the bar, the hole will experience a deflection in the y direction. So therefore, to maintain a steady flow of holes down the length of the bar, an electric field Ey is present. Or in other words, since we are keeping this wafer which is already connected to a potential Vx in a magnetic field, there will be an establishment of electric field Ey in the y direction. This is known as the Hall effect. The resulting voltage due to this electric field Ey is known as the Hall voltage. Now if we use the expression for drift velocity, v of x is equal to jx by q p 0, because we are considering holes, we could compute Ey, the electric field that is being introduced, which is equal to, or which should be equal to jx by q p0 into bz, where bz is the magnetic field. This can be rewritten as r suffix h, which is known as the Hall coefficient, which is equal to 1 by qp in this case. This is equally possible in case of electrons also. Though we are discussing this with holes, this is also possible with electrons. So in a nutshell, an Hall effect is an electric field that is being introduced when a connected semiconductor wafer is connected in a, or is placed in a magnetic field. So this is the basis of, or the basic idea of Hall effect. The concept of Hall effect helps us find whether a semiconductor is N-type or P-type. It will also help us find carrier concentration, calculate mobility of carriers, measure conductivity, and also helps measure AC power and strength of magnetic field.